Hi, today we're going to discuss about the binomial distribution. This is the lecture 5.1. So if you remember in our previous lecture, we discussed about the Bernoulli trial and a bit the binomial distribution. We're going to continue our discussions and we are going to consider two more distributions which involve the Bernoulli trial. One is called the geometric distribution and another is called the negative binomial distribution. So let me remind you first of all, what is the Bernoulli trial? So any random variable which takes the two outputs is called to be the Bernoulli random variable. So please note that there are many random variables which are the Bernoulli random variables. So far we've considered the example was the coin. When you toss the coin, you can have two outputs, either heads, either tails, right? But we've considered lots of other examples where there are many outputs, not just two. For example, when you roll a die, you can have the 6 different outputs, or when you count the number of the students who are coming to the lecture, there are going to be like many outputs, right? If the number of the students in your group is 40, then there'll be 41 outputs, starting from 0 until 40. Or if you basically count the number of the students who are watching the lectures, it is also going to be a random variable every time, right? But please know that for all of these examples where the number of the outputs more than 2, we can create the categories. For example, we can say, hey, when you roll a die, what is the probability of getting a number which is more than 3? Then this is going to be two categories, right? So you roll a die, you can get either number which is more than 3, either less than 3. Or for example, I can say, what is the probability of having a student number in the class more than 20? Then again, you're going to have two categories. Either the number of the students in the class is going to be more than 20, either less, right? You see, so we can create the categories. And what we want is, so we would like to create the scenarios when there will be always the two outputs. Either success, which is going to be denoted as 1, either the failure, which is going to be denoted as 0. We then know the probability of 1 success to be equal to the p, and the probability of 0 is equal to 1 minus p. So please note that 1 minus p is denoted as q most of the time. If you remember, in our previous lecture, we derived the formula for the binomial random variable. When we are going to do this experiment with the two outputs many times, and we would like to understand the number of the successful trials. So essentially, if I know that there will be 16 lectures in one semester, what is the probability that in 8 of them, there'll be more than 20 students, right? So this is exactly the binomial distribution when we are going to count the number of the times when we are going to have more than 20 students out of 16. This is the mass function for the binomial distribution. And what I want to know is whether this is the proper mass function. What I need to do is I need to take the sum, right? So if you have n trials, the number of the successful trials can be any number between 0 and n, right? And I can find the probabilities for any number of this x from 0 to the n. So what I have to do is I need to take the sum of the probabilities of x is equal to the k when k changes from 0 to the n, right? So please note that the number of the successful cases can be more than n or can be less than 0, right? And I'm just going to put the formula of calculating this probability. It is going to be the summation of k goes from 0 to the n. So c n k, p in the power of k, q in the power of n minus k, right? Exactly, I'm just using this formula, okay? So please note that this summation is nothing else than the binomial formula when you're going to expand the summation of the p plus q in the power of n. If you remember from the calculus course, if you have just the two letters here, a plus b, and the power of n can be expanded using this formula, okay? And please note that the p plus q is always equal to the 1, right? There are two outputs of the Bernoulli trial. One is p, one is q, and the sum should be equal to the 1. So that is why it is going to be simply equal to the 1. Then yes, this is the proper mass function. So we can legally use this function in order to evaluate the probabilities. Let's do an example. So let's say a bag contains 10 chips. 3 of them are red, 5 of them are green, 2 of them are blue. So we're going to choose 3 chips, one by one, with replacement. It means that every time I choose the chip, I'm going to look at its color and I'm going to put this back. So I'm going to do this process 3 times. What is the probability that exactly one of them is going to be red? Well, in this case, if I would just count the number of the red chips when I choose the 3, then this is going to have the binomial distribution, right? So please note that not many different, so this problem can be changed in any different ways. Like I can make this not with replacement, but without replacement. But in this case, it is not going to be binomial distribution. So it appears there are 3 important requirements to be the binomial random variable, and I'm going to list them now. So the first property is that for every trial, you're going to have 2 outputs always. There are 2 outputs. So essentially, you need to have the Bernoulli trial, Bernoulli random variable. The second is the P, the probability of success, should be the same for all of the trials. So the probability of success, which is P, is the same for all trials. It means that, so here, please note that when you choose the first bowl, what is the probability of choosing the red one? So you've got 3 red chips and 10 chips in total. What is the probability of choosing the red one? 3 over 10, right? Okay. So if you do this with replacement, then probability of choosing the red one from the second trial is the same, 3 over 10, because you choose one ball and you're going to put the same ball to put back to the box, right? And if you do this without replacement, then it is going to be different. So probability of choosing the red one is 3 over 10 in the first trial. Now let's assume that I've chosen the red one. What is the probability that the second time I will choose the red one? It is going to be 2 over 9, right? It is going to be different. So then in this case, the second requirement doesn't work. It is not going to be binomial, so that we cannot use the formula for the binomial distribution. So, and the third example, third requirement is the number of the trials, and the number of trials is fixed. Okay, so we can make this experiment many times, but our experiment is always choosing balls 3 times. We choose the 3 balls, then this is going to be our experiment. Okay, so the number of the trials is fixed. Then, so since all of the 3 requirements are fulfilled for this example, we can calculate the probability using the binomial distribution formula. So in this case, the probability of x is equal to the 1, because we need to have 1 successful trials out of 3. It's going to be equal to the c is 3, 1, times to the p, which is 3 over 10 in the power of 1, times to the q. What is the probability of choosing a ball which is not red? 7 over 10, right? 7 over 10 in the power of 2. Okay? So this is how we can calculate the probabilities for the binomial distribution. Okay? So there are a couple of properties here that the expected value for the binomial distribution can be calculated by just multiplying n to the p, and the variance can be calculated by just multiplying n pq. So there is an intuitive explanation. I mean, of course, there is a mathematical proof why the expected value is equal to the NP, but we can try to explain, but we can try to understand this intuitively. So let's assume that you can make a shot when you play basketball, and the probability of making this, let's say, is 60%. And if you make 10 shots, so what is the average number of the shots, the successful shots you can get? Intuitively. Right? So it's going to be equal to the 6. Or the same with the penalty. So if you try the penalty, and if the probability that you can make a goal from 1 penalty is 70%, then if you hit 10 penalty shots, then in average you should expect, not in average, you should expect to shot 7 goals, right? In average, you're going to shoot 7 goals, okay? So the expected value is going to be n times the p. So especially we can use this property in the following cases. So let's say a Gallup poll made a survey, and they asked 1,000, 2,000 1,236 adults whether they believe that bad luck follows if you pass is crossed by the black cat. And 14% of the respondents said yes, they believe to this. So by just taking this into consideration, if you would just expand the sample from 1,236 to the 2,800, what would be the number of the respondents which would believe to this? So which number of the respondents we would expect which would believe to this? We should multiply the n, which is 2,800, to the p, which is 0.14. Okay, so this is the expected number of the positive respondents, right? The respondents who believed this, we should expect. Okay, so we're going to discuss another variable which is connected with the Bernoulli trials. So the Binomial trial is just one experiment, one trial, when you're going to have two outputs. For example, you choose the ball and you would like to know whether this is red or not red. You choose the card, you would like to know whether this is ace or not ace. You come to the class and you would like to know whether there are more than 20 students or not. Okay? You see, so all of these are the examples of the Bernoulli trials. There are two outputs always. So now we played with the Bernoulli trial in the previously, right? So we said, hey, I would like to make this Bernoulli trial n times. Then I would like to count how many of them are going to be successful. The number of the successful trials out of n is going to have the binomial distribution. Now I would like to make a little bit changes. So I would like to now be interested to know how many trials we should do in order to get the first success. Right? For example, there are some students who are retaking the courses, right? So who are retaking, for example, the calculus courses, and I would like to know for one of you, what is the probability that like the student is going to pass the calculus course from the third trial? Okay, if the probability that he's going to make this from every trial is fixed, okay, it should be independent, is equal, for example, 20%. Okay, say small. Then I would like to calculate this. But I would like to do with another example. So let's say, suppose that you would like to try an English exam, so IELTS, and you would like to get 7 out of 9. So let's assume that your chances are pretty high, it's 70%. But still, it's probability, right? So it usually depends on the difficulties of the questions or the type of the topics which you have prepared and which you have in exam, right? So even though you prepared well, so if the topic doesn't match to what you prepared, so there is still probability that you will not be able to get the 7. Okay? So let's assume that you can get 7 with the probability of 70%. Now I would like to know what is the probability that you can make this from the third trial, exactly in the third trial, right? So what is this? So we need to make the scenario, right? We need to create the scenario. So what is the scenario? The scenario is you failed the exam in the first trial. You couldn't get 7. So let's say you've got 6.8. Is it a valid score in IELTS? Is it possible? Okay. So in the second time you fail this again. You've got 6.5. Okay. In the third one you made this finally, and you've got 7.5. Let's say. Okay, so this is possible scenario, and actually this is the only scenario to get this, right? You can't really change the places between Q's and P's. For example, if you change the P, like if you put the P to the second trial, it means that you made this from the second trial. You don't need to retake this again, right? So we stop when you succeed. We are going to try these experiments, Bernoulli trials, until you will get the success for the first time, okay? So the probability that you will get this from the third trial is going to be equal to Q in the power of 2 times the P. In general, probability of the number of the trials which you need in order to get the first success has the geometric distribution, and the probability of having K trials to get the first success is going to be Q in the power of K minus 1 times the P. And the explanation is that in all the previous K-1 trials, you have to get failure, and in exactly K's trial, you need to get the success. Okay, and this is the only scenario. If you remember, in the binomial distribution, we've got a combination of the p's and q's and the different powers, right? And we could just rearrange them. So that is why we always had this formula, the c, in front of this formula. But for the geometric, we don't need, because this is the only scenario when you're going to have one p at the end and all of the others are going to be q's. Okay, you can't really simply rearrange them. So again, the number of the trials which you need in order to get the first success is going to be called as the geometric random variable, and its probability mass function is going to be given like this. So I would like to do an example. So let's say you've got 9 balls in a urn. 6 of them are red, 3 of them are blue. What is the probability, by the way, of choosing a ball which is blue? 3 over 9, right? Or 1 over 3. Okay. So what do you think? So if you choose the ball, is it going to be the blue? We don't know. It's random, right? But we know that the probability of choosing the ball and it's going to be blue is 1 over 3 every time. Okay. Now what I want to know is, what is the probability that I will choose the blue? Okay. And it is going to be blue in exactly the fifth trial. So it means that I will choose the blue, that it's going to be red, then I will choose the I will choose the ball, then it's going to be again red, 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 then ball, then blue. Okay? What is the probability? So please note that the number of the trials which you need to do in order to get the first blue ball has the geometric distribution, and we can use this formula in order to make the calculations. Probability of x is equal to the 5 is going to be equal to the q and the power of 4 times the p. Okay, please note that 1 minus p is nothing else as the q. And probability of the q, probability of choosing a ball which is not blue, is equal to the 6 over 9, right? And the power of 4 times 2, 3 over 9. Okay? This is how we evaluate the probabilities if we would like to know the probability of having success in exactly specific trial. But most of the time, what we are required to find the number of the trials which we need, so the number of the trials is going to be either more than 5, either less than 5. Okay, so there are many different situations where we need to evaluate the probabilities. For example, when you need to get the first success and you need at least 5 trials or at most 5 trials. So in this example, when you've got like 3 blue balls and 6 red balls in a box, and you're going to do this experiment until you get the blue ball for the first time, what is the probability that you will need at least 5 trials? What does it mean, at least?
It means that 5 and more.
Yeah, it means 5 and more, right? So we need to find the probability of having the blue in the 5 trials, or in the 6, or in the 7, and so on, right? Probability of having this in the 5 trials, probability of having this in the 5, or in 6, or in 7, until which I need to continue. So it never stops. Okay, so theoretically I have to continue this until infinity. Okay, so at the first glance you might think that it is difficult to find this, because previously whenever we used to have this kind of sums, we found this using its complement, right? So do you remember what is the complement of this event?
It would be 1 minus
It is going to be 1 minus the probability of x is equal to the 0, 1, until 4. Right? So we can find this probability, right? So still we need to do a lot of calculations, but still it is possible, right? You can find the probability of x is equal to 0, 1, 2, 3, 4, just using this formula which is above, and subtract this from the 1. But it appears for the geometric distribution, it is easier to calculate the left-hand side rather than the left-hand side. Oh, sorry, the left-hand side rather than the right-hand side. Okay? It is easier to calculate this red term, sorry. So let's do this. So I would like to know what is the probability of having the first success in the fifth trial. It is q in the power of 4 times the p. Probability of having the first success in the sixth trial is q in the power of 5 times the p, plus q in the power of 6 times the p, and so on. Okay, you see, so all of the terms have the term p, and I'm going to take this out from the brackets, and the terms which are left inside the bracket are going to form something which is called a geometric series. So if you remember, the geometric series is obtained by multiplying the previous term to one to the same number, which is going to be called the common quotient, right? So here you can see that all of the next terms are going to be obtained by multiplying the previous term to the q, right? q5 is obtained by multiplying q4 to the q. q6 is obtained by multiplying q5 to the q, and so on. So this is going to be called as a geometric series, and this is not just the geometric series. This is the geometric series which is going to go until infinity, and it is going to tend to zero, right? Since the q is the number between 0 and 1, right? In the infinity, it is going to, its limit is equal to the 0. Okay? And for this kind of series, for this kind of geometric series, we've got a formula for finding the sum. The infinite sum is going to be equal to the first term, which is q to the power of 4, divided to the 1 minus quotient. 1 minus quotient. And please note that the 1 minus quotient is going to be equal to the same as the p, and this is going to be equal to the q to the power of 4. Okay? So you see, so it appears that it's easier to calculate this red part. It is simply going to be q to the power of 4. Okay? So what I want is that we can generalize this. So if you need to find the probability of having at least k trials in order to get the first success, it appears it is going to be simply the q in the power of k minus 1, right? We can create a formula, and we're going to write this down. So probability of having at least k trials is going to be q in the power of k minus 1. And its complement, which is x is less than k simply, is going to be q 1 minus q in the power of k minus 1. Okay, so please note that in this case there is no equality sign. So if I say what is the probability that you will need at most 5 trials, right? So you are not going to include the 5. If you include the 5, for example, if you need to find less or equal to the 5, then you need to use another formula. The probability of x is less than 6. Okay? Then this is going to be equal to the 1 minus q in the power of 5. Okay? So it is really important that whether you use the equality sign here or not. If you're using, then just take one number which is just like greater than this case. Okay? It's superbly important. So again, the geometric series has some properties. It has the property that its mean is equal to, say, 1 over p, and its variance is equal to the 1 over 1 minus p divided to the p squared. Well, does someone has a coin? No. Okay. So I just wanted to discuss this equation. Like the expected value is going to be 1 over p, and the variance is equal to the 1 minus p divided to the p squared. I just would like to know what does it mean, this 1 over p, okay? So let's say you would like to toss the coin, and the probability of having hats is equal to the 1 over 2, okay? So probability of having the hats is equal to the 1 over 2. So let's do this experiment. So I'm going to toss the coin, and I'm going to continue tossing this until I will get the first hat, okay? So let's assume that I've got all the hats in the first trial, and I'm going to immediately stop this game, and I'm just going to write down the result, comma. Then I'm going to make this experiment again. I'm going to start tossing the coin, and I'm going to stop this game once I've got the hats. So let's assume that you needed 3 trials. You've got the first hat, and exactly in the third trial. Stop the experiment and do this again. So in the third time, when I'm going to do this experiment, let's assume that I've got the first hat in the second trial. Okay, so 2. So the average of these numbers, which is the sum of the 3 divided to the 3, is equal to the 2, right? So which is nothing else as an expected value. So the expected value of the x, in this case, it is going to be 1 divided to the p, which is 1 divided to the 1 over 2, which is equal to the 2. Means that in average, you need 2 trials to get the first success. So for example, if the probability of having success in a single trial is 1 over 5, then the expected value is going to be equal to the 5. It means that in average, you need 5 trials in order to get the first trial, right? If you're going to do this experiment many, many times, then in average, you will need 5 trials. This is the meaning of the expected value, okay? let's do a couple of exercises. So one is going to be this exercise with the plane's engine. So let's say I've got an old plane and it is not going to start. So its engine is not going to start always. Probability that if I start the engine, it will launch is equal to say 1 over 4 only. Okay? So if the probability that I will launch the engine if I start this in a single trial is 1 over 4, what is the expected number of the trials I need to try in order to get the engine to be launched? What is the expected number of the trials? So I'm just going to use the formula. So the P, probability of having the first success, or probability of having a success in a single trial is 1 over 4. Then the expected value of the X is going to be equal to the 1 divided to the 1 over P, which is equal to the 4, right? It means that in average, I need to try 4 times in order to get the engine of this plane to be launched. Okay, so this is what does it mean, this E of X. Okay, we will do one more exercise. So let's say that suppose the company would like to hire a new worker. The probability that an applicant which is going to be interviewed is going to be hired is equal to the 0.6. Okay, let's say there are a bunch of people who came to the interview. Probability that each of them are going to pass the interview successfully is 60%. And this is the same for all of the applicants. And let's assume that the head of the company doesn't have a lot of time. Then if the interview was successful, then we're going to stop all of this process. We're going to hire this person and all of the others can go home. Okay? And we're going to make the interviews until we will get the successful interview. And the number of the people who should be interviewed has the geometric series, right? So if I would like to know what is the probability that I have to make 5 interviews, then I need to use the geometric distribution formula, right? Because so if I would find the new worker before the 5th interview, then I would just stop this there, okay? So what is the probability that 5 people should be interviewed? I mean, it is important, for example, for the secretary of the head of the company because she also needs to arrange the people who are going to come to the interview, right? And she can't really just call like a 15 people to come to the interview or like a 150, right? I mean, she's going to use this the probabilities or the expected numbers in order to know how many applicants should come to the interview. Okay, so the probability that the company is going to need 5 interviews, probability that the company is going to need 5 interviews in order to find a new worker is going to be equal to the q in the power of 4 times the p, simply. Okay, and the probability that a company needs at least 5 interviews is going to be simply q in the power of 4. Okay. Yeah, which is clear that the probability that a company needs at least 5 is going to be higher than exactly 5, right? Because p is a number between 0 and 1, so the multiplying q in the power of 4 to the p makes it smaller, okay? So now let's change the problem a little bit differently. So let's say the company needs to hire not just 1 worker, but 3 workers. So let's say what I would like to do is I would like to make the interviews. So in the following way, so the first person is going to be interviewed. If the interview is successful, then I'm going to proceed with the second. Then the second is successful. Then I'm going to continue this until I will get the third successful. Once I found the third successful, then I'm going to stop. Okay, you see, so in this case, there are many different scenarios. So it is possible that if I can do this like this, the first is successful, I'm going to write this. Like if you got just 5 boxes, okay? So let's simulate this with having 5 interviews. 1, 2, 3, 4, 5. Okay? So it is possible that it is unsuccessful, successful, unsuccessful, successful, successful, right? Or another scenario is it is successful, successful, unsuccessful, unsuccessful, successful, right? So you see, so in all of these scenarios, if you would like to find the probability of having 5 interviews only, right? Again, so we are looking for the probability of having the number of the trials, of having the third successful trials and exactly fifth trial. Because if I would find a third worker before, then I would stop this beforehand, right? So you see, in all of the scenarios, the last trial should be the P, okay? Because I have to stop in the fifth trial. It means that in the exactly fifth trial, I need to find the third worker, okay? So it doesn't matter what is going to be the scenario, the last one should be the P, okay? And still, if I would like to find the probability, I need to work with the previous the four trials, which is equal to the n minus 1. So in our case, or k minus 1, let's say, k minus 1, right? So k minus 1 trials. Then you see, so it doesn't matter in what is the scenario, the number of the successful trials is always going to be equal to the 3. It means that I need to have 3 p's, and the rest is going to be q, 2 q's, okay? And the number of the scenarios is going to be the number of the rearrangement of these 4 letters, not 5. Previously in the binomial, you had to rearrange all of the 5. Here you have to rearrange all of the 4 because the last one is fixed. And it's always going to be the P. Okay? What is going to be the number of the rearrangements there? So there are 4 letters, right? I need to rearrange 4 letters, and 2 of them are similar. Okay? So the number of the trials which you need in order to find the R success. So let's say I'm going to have the number of the successful trials should be equal to say 3, and I'm going to denote this as a 3. And the number of the trials in this case is going to be equal to the 5. Okay, the number of the trials here is going to be the random variable. You might need 6 trials in order to get the search success, or 10 trials in order to get the search success. And the probability of having exactly k trials in order to have the R success, it appears has the negative binomial distribution. And this is going to have the following formula. So it is going to be the combination of the n minus 1, of r minus 1, p to the power of r, q to the power of n minus r. And I hope that you understood the formula, right? So it is coming, again, from making the boxes and trying to figure out, right? So let's say, so you would like to simulate of having the R success in the case trial, right? So the number of the successful trials should be R. So it means that you're going to have P in the power of R. And the rest are unsuccessful. The rest is N minus R. So again, you've got, actually here it should be K here, right? In this formula, K and K and K. Okay, so in total, there are K trials. The last one should be fixed to be equal to the P, right? In a previous K minus 1 trials, how many P's you have? R minus 1, right? So you have a bunch of P's, P, 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 and the number of the P's actually is equal to the R minus 1, right? So if you remember, the number of the rearrangements of the K minus 1 terms is going to be the combination of the K minus 1, R minus 1, okay? This is the number of the scenarios which you're going to get with R P's and K minus R Q's when the last one is P, okay? So here are the 3 important distributions, the binomial, geometric, and negative binomial distributions, which all involve the Bernoulli trials. And they are really important because in many different situations in our life, we can simulate the things using the 3 distributions. So this is it for today. Thank you very much.